Welcome to ACE Online, ACE Engineering Academy. Alright students, now we are in the discussion of GATE 2026 Score Booster Series and the subject is Power Systems. Alright students, so in this session we are going to discuss some NAT type questions and MSQ type of questions, right? So we'll see some of the questions, right, in the given time. So we are going to discuss some little bit of questions only. See here students, first question, for an element in a power system, the positive, negative and zero sequence impedances are given as Z1 is equivalent to Z2 is equivalent to Z0 is equivalent to J1 per unit. Then the element will be the positive, negative and zero sequence impedance of the element are given, which are all are same. Z1 is equivalent to Z2 is equivalent to Z0 is equivalent to J1. Then the element will be, it is MSQ type, right? It is MSQ type, multi-select question. You can see option A, transformer. Yes, we know. For a transformer, Z1 is equivalent to Z2 is equivalent to Z0, right? We know that for a transformer, Z1 is equivalent to Z2 is equivalent to Z0. All the impedance are same, right? So that option A is correct. Option A is correct. Coming to the option B, an alternator with negligible armature reaction. If you see, for an alternator, the positive sequence impedance Z1 is equivalent to ZD double dash. ZD double dash, where ZD double dash is nothing but the leakage impedance plus the armature reaction impedance ZA double dash. You can write it as reactance XL plus XA double dash, right? When armature reaction is 0, the positive sequence impedance will be ZL, right? And the negative sequence impedance is Z2 is equivalent to ZD double dash plus ZQ double dash divided by 2, right? Where ZD double dash is nothing but ZL plus ZAD double dash and ZQ double dash is ZL ZAQ double dash whole divided by 2. Where ZAD double dash is armature reaction along the direct axis, ZAQ double dash is the armature reaction along the Q axis. They are saying that armature reaction along any axis is 0. Therefore, it is 2 ZL divided by 2, it is ZL. And the zero sequence impedance is directly is equivalent to ZL. Why? Because there is no armature reaction because of the zero sequence currents. So, the positive sequence impedance value is ZL, negative sequence impedance is also ZL, zero sequence impedance is also ZL. When armature reaction is negligible, Z1 is equivalent to Z2 is equivalent to Z0. Therefore, Z1 is equivalent to Z2 is equivalent to Z0 when armature reaction is negligible. So that option B is also correct. Option B is also correct. Coming to the option C, a transmission line with no mutual impedances. So you can see here, for a transmission line, what is the value of Z1 is equivalent to Z2 is equivalent to ZS minus ZM, right? When mutual impedance is 0, this value is equivalent to ZS. And the value of Z0 is ZS plus 2ZM. Whenever mutual impedance is 0, it is also is equivalent to ZS. Therefore, when mutual impedance are 0, we can write that Z1 is equivalent to Z2 is equivalent to Z0 for transmission line also, when mutual impedance are 0. So that option C is also correct. Coming to the last one, a static balanced star connected load. With neutral solidly grounded. Just you can see here students, whenever you are having neutral solidly grounded alternate any element, suppose if this is the star connected load, What is the positive sequence impedance of this one? The positive sequence impedance will be from here to here, here to here. Let it be R is the resistance of the load. You can take Z also, no problem, right? Therefore, the positive sequence network will be only the resistance up to the neutral point. So, this is phase A, phase B and phase C. So, that this is A point, this is the neutral point, this is R. If you see the negative sequence network, same. From A to the neutral point, the value of resistance is R. So, that Z1 is also R, Z2 is also R. And what about zero sequence network? Zero sequence network should be drawn up to the ground point, from A to the ground, from A to the ground. This is A, this is R, that will be R. The zero sequence impedance is also R. Now you can check here. Here I am calculating Z1 here, which is R. I am calculating Z2 here, which is R. I am calculating Z0 here, which is also R. Therefore, Z1 is equivalent to Z2 is equivalent to Z0. Got it right? So that for this also all are same. Therefore, option D is also correct. So what are the correct answers? All are correct. A, B, C, D. All are correct, right? A, B, C and D are correct. Alright students, that is the first question, right? So now see the next question here. Just here the next question, students. Just see the next question. So one of the easiest question related to the bus classification, right? And number of unknown quantities. Consider a 9-bus power system network and the synchronous generators are connected to buses 1, 2, 5 and 7. So it's a 9-bus power system network. Out of buses 1, 2, 5 and 7 are connected with synchronous generators. For a power flow study, as bus 1 is a slack bus, then there will be option A, 8 reactive power mismatches, option B, 5 reactive power mismatches, option C, 5 voltage as state variables, 5 voltage phase angles as state variables. It is also MSQ, multi-select question, right students? See, we are having 9-bus power system network, number of buses. N is equivalent to 9. And number of slack bus, there is one slack bus, that is bus 1. Number of slack buses, that will be 1, right? Number of PV buses, where generators are connected, those are the PV buses 1, 2, 5 and 7. In 1, 2, 5 and 7, 1 is a slack bus, so that remaining are only 2, 5, 7, right? So number of PV bus are 3. What are those? 2, 5 and 7. Remaining are PQ buses, number of PQ buses. It will be 9 minus 3 minus 1, it will be 5. Got it right? They are the number of PQ buses. Now number of unknown deltas. Number of unknown deltas as the state variables. How many deltas are unknown? Where delta is known, first of all? Delta will be known only at the slack bus. At remaining all buses, deltas are unknown. So that we can write this as n minus 1. It will be 9 minus 1, which is equivalent to 8. There will be 8 voltage phase angles. Deltas means voltage phase angles. There will be 8 voltage phase angles are state variables. They have given 5 voltage phase angles are state variables. So that D is wrong. D is wrong, right? Next one. Number of unknown voltage magnitudes. Number of unknown voltage magnitudes. Where voltage magnitudes are unknown, at every PQ bus voltage magnitude is unknown. Therefore, it will be number of PQ buses. Number of PQ buses. How many number of PQ buses are there? That will be 5. Therefore, how many unknown voltages are state variables? 5. 5 voltages as state variables. So, C is correct. C is correct. Next one. Number of known active powers. Active power equations. Where active power is specified? Every bus except at slack bus. Right? Only at slack bus you don't know P value. Remaining all PV buses and PQ buses, P is known. So that it will be n minus 1. It will be 9 minus 1, which is equivalent to 8. Therefore, there are 8 active power mismatches. Active power mismatches. Right? 8 active power mismatches will be there. Right? Means mismatch means calculated value and specified value, maybe there may be mismatch. That's why we have to go for the iterative next iterations. Right? Next one. Number of known reactive power equations. Where reactive power is known? Only at PQ buses. That will be a number of PQ buses. It will be 5. There will be 5 reactive power mismatches. 5 reactive power mismatches. So that A, B and C are correct. Right? A, B and C are correct. A, B and C are correct. Right, students? Right. Just go through that one. How we have calculated this. Now we'll see the next question. Yeah, similar type of question based on the bus classification only, but related to Newton-Raphson load flow method. Consider the power system network shown below. The size of the submatrices of the Jacobian matrix when the load flow problem is to be solved by Newton-Raphson load flow method in polar coordinates. They are asking the sizes of the submatrices of Jacobian. Submatrices of Jacobian are J11, J12, J21, J22. Right? They are given J11, J12, J21, J22. 4 options are given. It is also MSQ. It is also MSQ. See clearly. First of all, to solve this problem, first of all, do the bus classification. What is bus 1? At bus 1, voltage, magnitude and angle are known. So that bus 1 is a slack bus. Bus 1, slack bus. Right? Why? Because which are known here? V and delta is known. Bus 2, P and V are known. That's a PV bus. Bus 2 is a PV bus. Bus 3. See what is bus 3? Bus 3. Active power is known, reactive power is also known. Got it right? Active power is known, reactive power is also known. At bus 3, see here students. Here PG is equivalent to 1, QG is equivalent to 2. But there is no load. Therefore, you can take PD is equivalent to 0, QD is equivalent to 0. Therefore, at this bus, P3 is equivalent to PG minus PD, Q3 is equivalent to QG minus QD. Where PG is 1, 1 minus 0 is 1. And Q3, QG minus QD, 2 minus 0, it is 2. So that P3 and Q3 are known at bus 3. That's why it is a PQ bus. It's a PQ bus. Right. At bus 4, see clearly, Voltage magnitude is known. Okay. Active power Pg is known. Qg is also known. Pg and PD. Pg, PD are known. Therefore, we can calculate here at this bus P4 is equivalent to Pg minus PD, where Pg is 2, PD is 2, which is equivalent to 0. P4 is 0. But Qg is unknown. But Qd is known. When Qg is unknown, when Qd is known, it's not possible to calculate Q. Means Q is unspecified. It's possible to calculate, but Q is unspecified there. Got it right? But which is specified here? Voltage magnitude is specified. So that at bus 4, P and V are known. That's why bus 4 is also PV bus. Bus 4 is also a PV bus. PV bus. Got it right? So according to Newton-Raphson load flow method, you can write del P del Q is equivalent to the Jacobian matrix J11, J12, J21, J22 into delta delta and delta mod V. This is the Jacobian matrix, Newton-Raphson load flow equation. In this one, how many P's are known? How many active powers are known? You can write here it is n minus 1. Right, just previous problem only we have written. How many P's are known? N minus 1 P's are known. How many number of buses are here? 4 buses, right? Number of buses is equivalent to 4. Number of buses is equivalent to 4. N minus 1 means it will be 3. 3. How many Q's are known? Number of PQ buses. This is N number of PQ buses. How many number of PQ buses are known here? How many number of Q's are known? Q's are known, number of PQ buses. How many number of PQ buses are there? Only one. Bus 3 is the PQ bus. Only one. How many number of deltas are unknown? Unknown deltas. This is also n minus 1, which is 3. How many number of voltages are unknown? It is a number of PQ buses. It will be 1. It will be 1. Therefore, what is the size of J11? J11 is mapping del P with del delta. J12 is mapping del P with del mod V. J21 del Q with del delta. J22 del Q with del mod V. Therefore, the size of J11. What is the size of J11? N minus 1 cross N minus 1, which is nothing but it is 3 by 3. 3 by 3. J11 3 by 3. First option A is correct. Next one, J12. J12. It is mapping del P with del mod V. Right. Del P, it is N minus 1 cross del mod V NPQ. So it will be J11 3 cross 1. Sorry, it is not J1, J12. 3 cross 1. J12. 3 cross 1. B is also correct. C. J21. J21 is mapping with del Q with del delta. Del Q is 1, del delta is 3. It is number of PQ buses cross N minus 1. It will be J21 1 by 3. So J21 1 by 3. It is also correct. Option D, J22. J22 is mapping del Q with del mod V. It is number of PQ, number of PQ. Number of PQ buses cross number of PQ buses. So that it will be J22 1 cross 1. D is also correct. So that all are correct, right? So A, B, C and D all are correct for this question. So bus classification is very, very important, students. So with this bus classification you can understand very easily, right? It is given clearly. Bus 1 is a slack bus, V and delta are known. Bus 2 is a PV bus. bus 3 is a PQ bus, bus 4 is also a PV bus, right. Next question. The positive, negative and zero sequence reactances of 20 MVA 13.2 kilovolts synchronous generator are 0.3 per unit, 0.2 per unit and 0.1 per unit respectively, right. So, it is given that positive sequence reactance 0.3 per unit, negative sequence reactance 0.2 per unit, zero sequence reactance 0.1 per unit. You can write as the reactances, you can write J. The generator is solidly grounded and it is not loaded. It is operating under no load condition. When it is operating under no load condition, the EA1 per unit value, the pre-fault voltage both are 1 per unit. Whenever it is operating under no load condition. A line to line fault occurs. We are having a line to line fault occurs at the generator terminals. Then the line to line voltage VAB. They are asking line to line voltage VAB, right? And they are asking in kilovolts. So here line voltage V base line quantity, it is 13.2 kilovolts, and V base phase quantity, it is 13.2 divided by root 3 kilovolts. 13.2 divided by root 3 kilovolts. Fine. Now, for line to line fault, we are having IA1 is the negative of IA2 and VA1 is exactly equivalent to V8. VA1 is exactly equivalent to V8, right. Now just see here, in case of line to line fault, they are asking VAB. What is the value of VAB? It is VAN minus VBN. VAN minus VBN. What is VAN, students? VAN is VA0 plus VA1 plus VA2 minus VBN is VB0 plus VB1 plus VB2. They are the values of VAN and VBN. Here VA0 and VB0 will be cancelled. Zero sequence components are equal in magnitude and angle. Remaining are VA1 plus VA2 minus VB1 is K square times of VA1 minus K times of VA2. If we take VA1 outside, it is 1 minus K square. If we take VA2 outside, it is 1 minus K. As VA1 is equivalent to VA2, have written as VA1 is equivalent to VA2. Take VA1 outside, it will be 1 minus K square plus 1 minus K. This will be VA1 into 2 minus K square minus K. Students, we know that the value of minus K square and minus K is 1. 1 plus K square is equivalent to, you can write here, since 1 plus K square is equivalent to 0, 1 is equivalent to minus K and minus K square. So that in place of minus K square and minus K, I can write plus 1. Plus 1 and 2, it will be 3. Therefore, this is 3 times of VA1. That is the value of VAB. VAB value is 3 times of VA1. Now, VAB is equivalent to 3 times of VA1 is nothing but EA1 minus IA1 into Z1. EA1 minus IA1 into Z1. Calculate IA1 first of all, where IA1 is equivalent to EA1 divided by Z1 plus Z2. That is the positive sequence current formula for LL fault, right. So, this will be 1 per unit divided by Z1. Positive sequence impedance is given J0.3 plus J0.2. So, which is 1 by J0.5, it is minus J2 per unit. The value of IA1. Substitute the IA1 value here. Therefore, VAB is equivalent to 3 into EA1 is 1 minus IA1 is minus J2 into Z1 is J0.3. So J into J square minus, minus into minus plus, plus into minus minus. This is 3 into 1 minus 0.6. It is 3 into 0.4, which is equivalent to 1.2 per unit. That is the value of VAB in per unit. The value of VAB in per unit. What is the value of actual value? VAB actual value. It is VAB per unit value. VAB per unit value into VB phase. VB phase. Every time you have to use base phase values only. Right. VAB per unit is 1.2 per unit and VB phase 13.2 kilovolts divided by root 3. Calculate this one, students. Calculate this value. 1.2 into 13.2 kilovolts divided by root 3. Please calculate this value. You can get approximately 9.12 kilovolts. 9.12 kilovolts. 1.2 into 13.2 divided by root 3 kilovolts. That is 9.12 kilovolts. Right? See this type of problems. These type of problems are very, very important, students. Right? Calculating VAB for a line to line fault. Right. Right. The next question. See the next question here. A balanced star connected load is in parallel with a balanced delta connected capacitor bank. Right. So we are having star connected load and a delta connected capacitor bank. The star load has an impedance of Z star is equivalent to 3 plus J4 ohms per phase, and its neutral is grounded through an inductive reactance of Xn is equivalent to 2 ohms. The capacitor bank has a reactance of Xc is equivalent to 30 ohms per phase. Then, which of the following are correct? It is MSQ. So, it is given that we are having a star connected load and in parallel with a delta connected capacitor bank. Right. Here 3 plus J4 is given. Here also 3 plus J4 impedance. Here also 3 plus J4 impedance. Here also impedance are given. What are the values? Impedance values 30 ohms. It is minus J30 ohms. It is minus J30 ohms and it is minus J30 ohms. They are the impedance values of the capacitor. And the neutral is grounded through a resistor of reactance of 2 ohms. This is J2 ohms. Like that we are having the connection. Now, they are asking what are positive, negative and zero sequence values. First of all, draw the positive sequence network. To draw the positive sequence network, convert this delta into star. Convert this delta into star. Whenever you are converting the delta into star, this is the initial star connection, 3 plus J4. I am writing only in one phase. Here we are having the neutral reactance J2. Here, whenever you are converting delta into star, the star that you are going to get it is an isolated star. This is minus J. What is Z star is equivalent to Z delta by 3 for impedances. So it is minus j 30 by 3, minus j 30 by 3 and minus j 30 by 3. These are the impedances. See, I have written capacitors only, but I am calculating impedance. If I am calculating capacitors, C star is 3 times of C delta, okay. But I am calculating impedance, na? Z star is Z delta by 3, right. So, draw the positive sequence network, per phase this one, both are connected in parallel. Positive sequence network. 3 plus J4 in parallel with minus J10, right. Here I am calculating positive sequence impedance, Z1 equivalent value. What is Z1 equivalent? Which is 3 plus J4 into minus J10 divided by 3 plus J4 minus J10, right. If you calculate this value, we are getting this as 6.67 plus J 3.33. That's what we are going to get. 6.67 plus J 3.33. So that positive sequence impedance values are correct. Option A is correct. And what about negative sequence also same only? No change. Why? Because all are balanced loads only. In every phase we are having same values only. So positive sequence, negative sequence impedance are exactly same. So that this is also equivalent to Z2 equivalent. Z2 equivalent. While drawing zero sequence network, I will draw here zero sequence network. First one is neutral reactance grounded, and second one is neutral isolated, right. You can calculate Z0 equivalent here. This is 3 plus J4 and this is 3 times of J2, right. It is J6, J4, it will be J10, 3 plus J10, right. So A is correct, the negative sequence impedance also same, B is correct, the zero sequence impedance is 3 plus J10, C is also correct. D is the zero sequence reactance is 3 plus J4, that's wrong. So A, B, C all are correct. Option A is correct, option B is correct and option C is also correct. Do the calculation properly. Do the calculation properly. Alright students. Right. Coming to the next question. A 50 Hz 100 MVA synchronous generator is having an inertia constant of 7 megajoules per MVA and is capable of supplying 400 megawatt of power, is connected to a large system and it is delivering 80 megawatt when a three-phase fault occurs at its terminals. Then the time in which the fault must be cleared if the maximum power angle is to be 85 degrees. A question related to equal area criteria, transient stability analysis. Right. See, it is given that the synchronous generator is having an inertia constant H is given. Inertia constant H. It is given that 7 megajoules per MVA. 7 megajoules per MVA. Megajoules per MVA. And frequency is given 50 Hz. And the apparent power value is given 100 MVA. S is given 100 MVA. And it is capable of delivering 400 megawatt. So where P max 1 maximum power it can transfer is 400 megawatt. But out of this, it is delivering only 80 megawatt, where PE is equivalent to PS, means PE1, PS. PE1 and PS. Both are 80 megawatt, the initial power. Initially, before the disturbance, the mechanical input and electrical power output both are same. Both are 80 megawatt. So when PS is equivalent to P1 is equivalent to 80, we can calculate delta naught. What is the value of delta naught? sine inverse of Ps by P max 1. This will be sine inverse of Ps is 80 divided by 400. 1 by 5, 0.2. Sine inverse of 0.2. Sine inverse of 0.2. Calculate that sine inverse of 0.2 value, students. Sine inverse of 0.2. So you'll get 11.54 degrees, which is equivalent to 0.2 radians. 0.2 radians. That is the value of delta naught. And delta max is given. What is the value of delta max? 85 degrees. And what is the radian value? The radian value of this one, you will get it as 1.22 radians. Right, 85 degrees and 1.22 radians. That is the value of delta max. Once you got this one, they are asking critical clearing time, the time in which the fault must be cleared. Right, critical clearing time. The critical clearing time Tc is equivalent to under root of 2m into delta C minus delta naught divided by Ps, which is equivalent to Pa. Electrical power is 0 under the fault condition. 2m into delta C minus delta naught. Calculate delta C, critical clearing angle. It is cos inverse of Ps into delta max minus delta naught in radians plus P max 1 cos delta max divided by P max 1. Why? Because the fault is at the terminals of the generator. The fault is at the terminals of the generator. See this case study. The last case study we have taken, right? Fault at the terminals of the generator. It is cos inverse of Ps is 80 megawatt and delta max 1.22 radians, delta naught 0.2 radians, P max 1 400 megawatt into cos of delta max in degrees 85 degrees whole divided by P max 1 400 megawatt. Calculate this one, approximately you are getting this as 69.9 degrees. 69.9 degrees, right? And the radian value, right? The radian value here, sorry students, just this is not 1.22, this is 1.48. This is 1.48. Substitute that, this is 1.48. And the resultant value, this value is 1.22. This value is 1.22 radians. Change that one. Now, once you got this delta C value, substitute this delta C value in the Tc value. Calculate Tc, students. Therefore, the value of Tc is equivalent to under root of 2 m is s into h divided by pi into f into delta C minus delta naught divided by Ps under root. Substitute that, students. It will be 2 into s is 100, h is 7, pi into 50 into delta C in radians. It will be 1.22. Delta naught in radians, it is 0.2 divided by Ps, 80 megawatt. 80 megawatt. Right. You will get in seconds. It will be approximately 0.337. 0.337 seconds. Please check it clearly. That is the value of critical clearing time. Critical clearing time. So you have to definitely remember the formulas of Tc and delta C. Then only it will become easy. Otherwise, we need to go for the integration. Right. So we'll see the next question here. Students. Yeah. So question from transmission and distribution part. For the power system network shown below, VA is equivalent to 220 cos omega t plus 30 volts, VB 220 root 2 cos omega t plus 15 degrees volts, and VC 400 sin omega t. 400 sin omega t. Write them in phasor form. VA. VA is 220 cos omega t plus 30. It will be VA is 220 by root 2 at an angle of 30. That is VA value. What is the value of VB, students? The value of VB 220 root 2 cos omega t plus 15. 220 root 2 divided by root 2, it is 220. VB is 220 at an angle of 15 degrees. And VC 400 sin omega t. VC is 400 cos of omega t minus 90 or cos of 90 minus omega t. Right? 400 cos of omega t minus 90 or cos of 90 minus omega t. Both are same. Cos of minus theta is cos theta. Right? It will be 400 divided by root 2 at an angle of minus 90. At an angle of minus 90. Like that you can write. Just see. This is inductive medium. This is capacitive medium. In inductive medium, active power always flows from high delta to low delta. I will write the statement. In inductive medium, active power flows from high delta to low delta. That is high voltage phase angle to low voltage phase angle. And reactive power always flows from high voltage magnitude to low voltage magnitude. Right? Please check it. Here, voltage is 220 by root 2. Here it is 220. The active power is flowing in this direction. High delta to low delta. High delta to low delta. This is 30 degrees. This is 30 degrees. This is 15 degrees. This is the direction of the active power. High delta to low delta. Reactive power flows from high voltage to low voltage. Here it is 220. Here it is 220 by root 2. This is the direction of the reactive power. See, PA direction, P direction both are same. So that PA will be greater than 0. PA should be greater than 0. PA should be greater than 0. Okay, option A and option B. Both are correct. And QA. What about QA? QA is also greater than 0. No? So Q direction, QA direction both are same only. QA should be greater than 0. QA is also greater than 0. Okay. On the other side, in case of capacitive medium, exactly opposite. I am not writing that one. In case of capacitive medium, active power flows from low delta to high delta, right? And reactive power flows from low voltage magnitude to high voltage magnitude. So just check it here. So in case of capacitive medium, active power flows from low delta to high delta. Here it is minus 90, here it is 15. This is the direction of the active power. So PC should be greater than 0. Given direction and P direction both are same only. So that PC should be greater than 0. So that option B may be the correct answer. We have to see. So PA greater than 0, PC greater than 0. And PB, just here, both the powers are entering, but PB is moving in the upward direction. PB should be less than 0. So that B is correct. B is correct. Right. And what about the reactive power here? It is flows from low voltage to high voltage. This is the direction of the reactive power. The direction of reactive power, students. This is the direction of the reactive power. See here, the direction of the reactive power. Low voltage to high voltage. QC should be greater than 0. QB should be less than 0. Right? So QC should be greater than 0, QB should be less than 0. QA greater than 0, QA greater than 0, yes, QA greater than 0, QC greater than 0, QB should be less than 0. QB should be less than 0. C. So both B and C are correct. B and C are correct. Please check it clearly. QA should be greater than 0, QC should be greater than 0, low voltage to high voltage, right? And QB direction and Q direction, both are in opposite direction. QB should be less than 0. Got it right? Perfect. So B and C are correct, right? So it is also MSQ, right? See the next question, students. Yeah, again from transmission and distribution. The nominal T circuit of a transmission line is shown in the figure. So the nominal T circuit of the transmission line is shown in the figure. Y1, Y1, Y2 are given. The series admittance Y1, is given 0.005 mho per kilometer, and the shunt admittance Y2 is 0.01 mho per kilometer. The propagation constant gamma of the transmission line will be, right? Actually, T circuit means we should have the T circuit like this, right? It should be Z by 2 here in ohms. Here it is also Z by 2 in ohms, and here it should be Y. Like that we should have. But in place of Z by 2 in ohm, they have given Y1 in mho, right? Therefore, we can write that Z by 2 is 1 by Y1. Z by 2 is 1 by Y1, where Z is equivalent to 2 by Y1. Y1 is given 0.005. It is 2 by 0.005 ohms now per kilometer value. Got it right? And Y is given Y1, Y2 directly. Y is given Y2 directly. It is 0.01. 0.01 mho per kilometer. They are asking propagation constant, root of Z into Y per kilometer values. This is per kilometer value, this is per kilometer value Z, this is per kilometer value Y. Right. Substitute that value, students. It is 2 by 0.005, 2 by 0.005 into Y, 0.01. So it will be 0.02 divided by 0.005. You can write it as 2 by multiply with 1000, 20 divided by 5. 20 divided by 5, it is under root of 4, which is nothing but 2. The propagation constant for this problem is 2. Got it right, students? Right. So again, a very simple question. The propagation constant. Right. Right, students. The next question we can see here. Just see the next question. From the protection part, power system protection. Consider the distribution network shown in the figure. For relays R1, R2, R3, R4 are having proper coordination, right? They are having proper relay coordination for the reliable operation. For the fault at location F, so here we are having the fault. This is the fault location. Which of the following statements are not correct? They are asking not correct statements. See, here, first statement, relay 2 will have high pickup current than that of relay 4. Just see clearly, very easy question. Relay 2 is here, relay 4 is here. Relay 4 is close to generator, relay 2 is away from the generator. So, first who has to sense the fault? Which relay will see less currents? Relay 2 will see less currents, relay 4 will see more currents. That's why the pickup current of relay 2 should be less than that of relay 4. The pickup current of relay 2 should be less than that of the relay 4. Why? Because relay 2 has to sense the fault first, right? Later on relay 4. Why? Because relay 4 will be backup for relay 2. Got it right? So, first statement is given, relay 2 will have high pickup current than that of relay 4. No, this is wrong statement. This is wrong statement. Second one, relay 1 will have high pickup current than that of relay 3. Relay 1 will have high pickup current than that of relay 3. Yes, relay 1 is close to generator, relay 3 is away from the generator. Definitely, relay 1 will have high pickup current than that of relay 3 default. So that this is correct. This is correct. Next one, relay 1 will have high operating time than that of R3. Relay 1 will have high operating time than that of, no. When relay is close to the generator, the faults which are close to generator are always more severe faults. So that those relays should be operating faster. Relay 1 is having the least operating time than that of relay 3. Pickup current of this one is less. Operating time of this one will be less. Got it, right? So relay 1 will have least operating time than that of relay 3. So relay 1 will have high operating time. No, this is also wrong statement. Next one, relay 1 will have low operating time than that of relay 3. Okay, option D is correct. But they are asking incorrect statement, no? So A and C are incorrect, right? A and C are incorrect. They are asking incorrect statements. For this one, A and C is the answer. A and C is the answer, right? They are asking incorrect statement, right? Please check it clearly. Please check it clearly. Right, students? The next question, for the network shown below, the capacitor connected at the load side supplies a reactive power of 0.85 per unit. Then the reactive power supplied by the source Qg in per unit will be. See here, students, here we are having 1 at an angle of delta, here we are having 1 at an angle of 0, here we are having a capacitor Qc. The load is unity power factor load, where load power is 1 per unit. Here also we are having one load, it is asking a demand of active power of 4 per unit, reactive power of 2 per unit, right? Okay. Now see clearly, whenever we are writing SR, which is equivalent to PR plus J times of QR at this point. Right, students? What is the value? PR. PR should be equivalent to PD. PR is equivalent to PD. How much it will be? 1 per unit. And QR plus QC. QR plus QC must be equivalent to QD. QD is how much? 0. The load is a unity power factor load. QD is equivalent to 0. Therefore, QC is equivalent to minus QR. How much it is QC given? 0.85. 0.85. QR is equivalent to minus QC. You can write it as QR is equivalent to minus QC. QR is equivalent to minus QC, which is minus 0.85 per unit. Means capacitor is supplying reactive power to the line only, not to the load. In this direction, see clearly, in this direction, reactive power is Q is equivalent to minus 0.85. Minus 0.85 per unit. In this direction. So, in this direction it will be positive, no? Therefore, from this bus, the reactive power that is coming to the line, it will be plus 0.85 per unit. Got it right? When both side voltages are same, I told you already, in a reactive medium or inductive medium, reactive power always flows from high voltage to low voltage. Just in the previous question you have seen, reactive power always flows from high voltage to low voltage. High voltage magnitude to low voltage magnitude. But here both side voltages are same only, na? When both side voltages are same, right, and in between line is reactive, for this reactive line, it needs some reactive power. The reactive power for this line will be supplied equally by both the buses. Means from this bus also, the reactive power should be 0.85 per unit. When both side voltages are same, both the buses will supply equal amount of reactive power to the in between inductive transmission line. So, from this bus, the reactive power supplied to the line is 0.85. Now, calculate the reactive power here. How much amount of reactive power Qg is equivalent to? Qg is equivalent to 2 is flowing to the line and 0.85 is flowing to the line. 2 is flowing to the load, 0.85 is flowing to the line. It will be 2.85 per unit. No need of any calculation. You can give the answer directly. 2.85 per unit. Got it right, students? Very simple question. You can expect this type of questions for 2 marks. Very, very, very simple. Without any calculation you can give. Right, students? Right. So we'll see one more question here. Yeah. A 50 Hz lossless long transmission line is having a series inductance and shunt capacitance of 0.02 Henry per kilometer per phase and 0.0012 microfarad per kilometer per phase. So we are having inductance and capacitance values. So frequency is given 50 Hz. Inductance is given 0.02 Henry per kilometer per phase. And capacitance is given 0.0012 microfarad per kilometer per phase. Right. This line is connected with a pure resistive load, right? And which is equal to the surge impedance loading. So that line is loaded with the surge impedance loading. The voltage phase angle delta difference between sending end and receiving end voltages after 400 kilometers length of the line. Just see here, students, we are having a transmission line of 400 kilometer length, where L is equivalent to 400 kilometers. Right. So here we are having the source, and here we are having a pure resistive load. Right. Here the source voltage is Vs at an angle of delta. Here the load voltage is Vr at an angle of 0. The line impedance is Zc. Here it is also, they are saying it is Zc. Line is loaded with surge impedance loading. Zl is equivalent to Zc. Zl is equivalent to Zc. When Zl is equivalent to Zc, Vr is exactly equivalent to Vs. Therefore, Vs at an angle of delta is nothing but Vr at an angle of 0. Vr at an angle of 0. So that we are going to calculate the value of delta here. Right. And you can calculate, if you calculate this delta value, the delta value is equivalent to beta L you are going to get. Right. We have done the derivation in the class. The value of delta is equivalent to beta L. Got it right? Means Vs at an angle of delta is equivalent to not Vr at an angle of 0, it should be Vr at an angle of beta L. That's the perfect way to write. Vs at an angle of delta is equivalent to Vr at an angle of beta L. Then delta is equivalent to beta L. That's the perfect way to write, not 0. Right. If you write 0, delta is equivalent to 0. That's not correct. Delta is equivalent to beta L. What is beta for lossless line? Beta is nothing but omega root Lc into line length. They are asking delta. It is 2 pi into 50 into root Lc. L is given 0.02 Henry into 0.0012 microfarad into 10 power minus 6 into 400 kilometer. We will get this value in radians. Why? Because beta is in radians. Convert into degrees, students. 180 by pi. Calculate this value. 2 pi into 50 into under root of 0.02 into 0.0012 into 10 power minus 6 into 400 into 180 by pi. Into 180 by pi. You will get this value approximately 35.27 degrees. 35.27 degrees. Got it right, students? So like that you can get the value of delta, the phase angle difference between sending end and receiving end, when line resistance, reactance and capacitance are given. Right? Yeah. So we'll see one more question here. Two identical alternators, each rated for 150 MVA, 33 kilovolts are connected in parallel. One of the generator neutral is isolated and the other generator neutral is solidly grounded. The positive, negative and zero sequence reactances of the alternator are J 0.5 per unit, J 0.4 per unit and J 0.05 per unit. respectively. For a single line to ground fault at the terminals of the alternator, the voltage across the neutral of the isolated neutral will be, right. We are having an LG fault, students, single line to ground fault. For single line to ground fault, the voltage across the isolated neutral. So we are having a LG fault here. Two identical alternators, each rated for 150 MVA, 33 kilovolts are connected in parallel, right. So you can see here two alternators which are connected in parallel. Alternator 1 and the second alternator. One is star solidly grounded, one is star isolated. Positive, negative and zero sequence reactance are given for them, right. Now, if you draw the positive sequence network, will be, so this is the positive sequence network. Here you can calculate X1 equivalent. What is the positive sequence impedance? J 0.5 given. It is J 0.5. It is also J 0.5. It is J 0.25 per unit. That is the positive sequence value. See the negative sequence. Negative sequence network. This is J 0.4, J 0.4. Here you can calculate X2 equivalent. It is J 0.2 per unit. See the zero sequence network. The zero sequence network will be, first one is solidly grounded, second one is neutral isolated, right. So it is J 0.05. So that X naught equivalent is J 0.05 per unit. That is the value of X naught equivalent. Fine. Now, for LG fault, you have to connect all the three sequence networks. The positive sequence network, and negative sequence networks you can connect here, and the zero sequence networks. This is the connection we are having. That is the sequence network for LG fault, right. So that you can calculate IA1 here. What is the value of IA1 is equivalent to? IA1 is EA1 divided by X1 equivalent plus X2 equivalent plus X naught equivalent, where EA1 is 1 per unit, X1 equivalent. What is the value of X1 equivalent? J 0.25 plus X2 equivalent is J 0.2 plus J 0.05. So it is 1 by J 0.5 per unit. It is minus J2 per unit, right. Same current will be flowing here, minus J2 per unit. And this minus J2 will flow through this path, minus J2 per unit. This reactance is J 0.05. Therefore, the voltage across this one will be V is equivalent to J 0.05 into minus J2. Calculate that value, students. Therefore, voltage across the neutral Vn is equivalent to J 0.05 per unit into minus J2 per unit. J into J, J square minus, minus into minus plus. 2 5s are 10, it is 0.1 per unit. They are asking the actual value. Voltage across the isolated neutral, this total voltage will appear here. Same only, open circuit voltage will be, the total voltage will appear across this one. Therefore, the neutral voltage is 0.1 into VB phase. It is 0.1 into, you will get 33 divided by root 3 kilovolts, right. So approximately this value, you can get this value, students, 33 divided by root 3. You can calculate this value, just a minute. You can see this value as 1.91 kilovolts, 1.91 kilovolts, right. That's the value. Right, students, these are the some of the questions we are having in the power systems, right? And we are having pre-gate 2026 series, students. It starts from 18th January, right? So we are having an examination, pre-gate examination. So forenoon session for CE and instrumentation, as well as ME and CSIT. In afternoon session, EC, PI and EE and DA. For electrical engineering students, so on 18th afternoon session we are having pre-gate examination, right? And we are going to start a revision series, GATE 2026 revision series, which starts from 10th January, students, right? Just you can scan this QR code, you can join the course, right, students? That's all for today's session. Thank you, everybody.